Hello, my name is Kyle Hammond, and I'm going to be covering milling for quality for the Virginia Education Center for Asphalt Technology today. As an overview of topics, we're going to cover a list of different things that affect our finished product, the finished product being the milled surface. We're going to cover some topics that we don't consider as much as we should, some more obvious and some that we just fail to consider as we move from job to job and site to site. So we'll start with the environment and machine maintenance, machine configuration, and move into operating practices. We'll end with drum configuration. But just as a beginning point, let's go with terminology, because every manufacturer lists these components by a different name. Just so we're consistent and we understand what these components are, I'm going to define them for you for the purpose of this presentation. First, that is the secondary conveyor. That's going to be your conveyor that discharges material out onto the dump truck. Your primary conveyor is going to unload material from the cutter housing and move to the secondary conveyor. That would be the cutter drum. Then we have our front and rear mold boards, and those are our end gates, the end gates on the immediate left and right hand side of the cutter drum. Next, we'll define what we mean with grade and slope control systems, because these can vary pretty drastically. The most basic would be your 2D control system that you see on most machines out in the field. And 2D control systems are using sensors, either wire rope sensors on the end gates on the older machines, and newer machines will have sensors in the hydraulic cylinder there that lifts and lowers the end gates. Averaging systems are going to be sonic sensors that send sound pulses to the ground and measure the time it takes for the sound to travel to the ground and back to the sensor itself. These sensors are going to be placed on each side of the machine or one side of the machine, and a number of sensors are going to be sending these sound pulses. Now the measurements are going to be averaged. That way, when there is an outlier or a large component that could throw off the measurement, it's going to be averaged among 3 different sensors, as opposed to one sensor that could see something and cause the machine to make a real drastic correction that wasn't absolutely necessary. Again, on the averaging systems, when you should use sonic sensors, that's a good question of when you should use them. They don't always have to be averaging. You can use one sonic sensor as a means of reference. And a great time to do that would be when you're off on a shoulder or something where you don't have a sound surface for the end gate to ride on. If the end gate doesn't have a sound surface to ride on and is very uneven, then you can switch to a sonic sensor. A sonic sensor can be placed over here in front of the front mold board like you see here. That's a good time to do that when you're off on the shoulder. 3D control systems. Oftentimes these are required for airports. These require additional equipment that you might see more in the surveying field. But this is excellent technology. It's within millimeters of accuracy, but it doesn't come without a learning curve. So I would recommend when these jobs are requiring 3D milling or this sort of technology that you have someone from your local provider, such as Topcon, a Trimble, a Leica. These are manufacturers of this system. It's a good idea to have someone from there on your site to make sure that you've got everything hooked up properly and everything's working right. This is it seems like one of the more obvious topics, but it's something we often forget, is do I have the tools I need for the job that day? And as you all know, the one day you don't consider something, such as safety equipment, is the day you have an accident. So first and foremost, let's make sure we have all our safety equipment. On top of that, let's make sure we have all the other tools we need. Do we have extra teeth? Do we have all our maintenance tools? Do we have the job laid out properly? Do we have the level? Do we have the paint stick? All the other tools that are needed to properly perform this job. So control points. Here is an excellent case of what not to do. One gentleman was actually having some fun with the other guys on the crew that day when he laid out this pass in this manner. So we don't want to do that, but we do need to properly lay out the job. We need to tell the crew where we're going to start and end each pass, how many passes we're going to make. We need to identify our obstructions. We need to lay the job out as part of our game plan. Now, the ground man is a key part of job layout and then carrying out the game plan. The operator obviously has his hands full, no pun intended. The ground man is also in charge of some very key things, such as maintaining zero, identifying obstructions, communicating with everyone on the crew of what's about to come up, what's going to happen. There might be times where we need to switch our grade reference, switch sensors, usually move to a different application. That's going to be his call, and he has a very big responsibility in that regard. Calibrating sensors, again, when we covered the grade control systems, this one is going to be largely up to the ground man to calibrate the sensors. So at the beginning of the day, we lower the machine down until the teeth barely scratch the surface. And at that point, we zero the machine. Zero being a verb to signify that we have told all the sensors where zero is. Now that we've told the machine where zero is, the machine doesn't know anything else other than where zero is and where it is at that moment. So when you check zero on like a second pass, when we make a second pass, one side will read zero, one side would read whatever cut depth. Let's say we set the cut depth at 2 inches. On your first pass, you would have 2 inches on the left-hand and right-hand side showing on your grade control system. On your next pass, the side that's already been milled would show zero. The side you haven't milled is going to show whatever selected depth, 2 inches. So at each pass, the ground man is going to continuously check zero, make sure that the sensors are maintaining calibration, and we're getting the grade that we need. That's just another picture of where to check zero. If these joints didn't line up properly, if one was below the other or above the other, we would know something was incorrect. We didn't hit zero on one side, something's out of whack. Another responsibility of the ground man is to know the surface condition, like what we see here. How do you approach this type of surface? Well, the answer to the question, before I give you the question, is to slow down and put pressure on the front mold board. The reason we do this is when you see a road surface that's deteriorated in this manner, which is fairly common, if you are moving too quickly and you don't have enough pressure on the front mold board, slabs of material like you see here will just rip up into the machine. That's going to damage the conveyors, and it's going to ultimately create downtime. That's a big deal, especially when you have several trucks of hot mix asphalt and a paving crew right behind you that are preparing to pave. If the milling machine's down, we have an issue. We can avoid this by slowing down, applying pressure to the front mold board, and processing the material slower, so we're not throwing huge slabs of material in, doing damage. Job site obstacles. The picture on the left is only slightly exaggerated. Those of you that do a lot of milling and paving for that matter know that that's closer to reality than what a lot of us would admit. Those of us that are just driving or walking along don't realize how many obstacles there are in the paved surface that we have to account for when we mill and pave. So again, these are obstructions we have to account for and we have to fill into our game plan. On the right, you see a tree here that was ripped out by a milling machine, and that should have been a part of the game plan. We should have accounted for these low-hanging trees. Perhaps we could ask for another lane closure, temporary, until we get through these trees. We could offset our dump truck, move our conveyor, try to minimize the damage. Most agencies or DOTs or local inspectors will work with you because as painful as an additional lane closure might be, they're not going to be happy when a bunch of their pretty trees are ripped out of the ground either. So let's try to find a solution to these problems before we get started each day. This one rolls into, do we have the right tools for the job and the obstructions? If you're in an urban area and you have a lot of these manholes, there are different machines that are capable of milling these obstructions and making life a lot easier and giving you additional clearance so that you're making it a little easier for the bigger machines to maneuver around. So we'll shift gears a little bit and talk about why it's important to keep the surface clean. And there are a couple of different reasons. The main one that everyone knows, we have to keep the surface clean so that the tack coat is applied properly and it adheres to the new hot mix layer properly. Also, we talked about how we zero the sensors out at the beginning of the day and how the machine only knows what 0 was at the time we nulled the sensors. Now, let's say one of our in-gate sensors or one of our sonic sensors rolls over these rocks here. Well, to the sensor, that is the surface. That's what you told it was the surface. It's not the actual surface, it's just debris. So if we don't clear that obstruction, now we don't get the proper grade that we were seeking when we began. So all this debris is going to throw off our grade. We have to keep it clean. At the end of each pass, we're going to have a lot of material built up in the cutter housing. It's just a little bit inevitable, but it's on the broom operators and the ground crew to make sure that the in-gates don't travel through this material. Sometimes we think we can add down pressure to these in-gates and it will just plow through, but that is very poor practice. We should just make sure that this is clean. Make sure that the pathway of our sensors is always the surface that we want it to be. Now we'll jump into tooling maintenance and how that affects our milled surface. On the left is, I guess that's a picture of when drum tooling is so neglected that you get a milled surface that's not even really describable. This is more common. When you have a broken tooth or a holder, a tooth that's fallen out, what have you, you'll have that white line that you see, the streak down the milled surface, and that means it's time to stop and check teeth. This is a nice diagram of how the cutter teeth wear. As you know, the drum's filled with a number of teeth that actually remove the asphalt. Those teeth they have a water system in the cutter housing. That's going to reduce dust. It's also going to reduce heat. As you would imagine, when these teeth are slamming into the asphalt, that creates a tremendous amount of heat. So in order to control that, they're spraying it with water, but also these teeth rotate in order to mitigate that heat that's created, because these things would essentially just burn down, melt away. They would wear in a very quick manner. So let's assume that our water system's working well and that the teeth are maintaining a rotation. In a perfect world, this is how your teeth will wear. And you can see, once you get over to the right-hand side, that even if the teeth wear perfectly, what happens? The surface area is much larger. So when the surface area is much larger, how does that impact us? We're going to see a huge production loss because the surface area is bigger. The same engine with the same horsepower is having to move a much larger surface area through the asphalt in order to remove it. So we're going to see a fuel economy drop, and we're also going to see a production loss in foot per minute. So it's important to watch our tooth wear in terms of our milled surface, but also it behooves us to remove them, in a timely manner once they're worn. Otherwise, the whole project's going to suffer in one way or another. Once a tooth is worn too far, let's say we've gotten past stage 4 and it's worn, then we get into the holder. The holder is where the tooth is seated down within the drum. Once you start to wear down the holder, you might not even notice it. You knock another tooth in. Now you've changed the orientation of the tooth, how the tooth is supposed to be seated. And that's when you start a new pass and you see a jagged surface there. And the paving crew is not going to be too happy with that, having to start a new pass with that to work with. So from there we'll jump into drum configurations and line spacings, tooth spacings, drum RPM, lacing patterns. Some of these are very interrelated, but we're going to talk about how the different drum configurations can affect our milled surface. This picture here is from an old Astec technical publication, but it shows the different tooth spacings that we've come to know the drums by, and then what surface we should expect and why we call them that spacing. 3/4 inch excavating, that's more of a reclaimer stabilizer drum. That's not typically seen on milling machines. A 5/8 inch, that's the industry standard for the most part. That is far and away the most common tooth spacing we're going to see out in the field. And then you have a profiling drum. We call profiling, anything between 5/8 inch and 2/10 inch. 2/10 of an inch is a micro milling pattern. Micro milling typically done when we have a very, very thin overlay of asphalt that's coming, because we can't, the thinner the overlay of asphalt, the finer the surface needs to be. If you were to try to overlay this rough texture with a very thin layer of asphalt, this surface would mirror through, and we wouldn't be achieving much. We'd have a newly paved rough surface. So this is what we mean with 5/8 of an inch. We mean if we were to measure, if we were to sit this drum down, and in one rotation of the drum on the surface, we would have a peak-to-peak and valley-to-valley measurement of 5/8 of an inch. This is what a 5/8 inch standard drum, triple wrap drum, looks like at 30 feet per minute. This is a milled surface that's fairly uncommon for the wrong reasons, but it's because we don't see many machines with a 5/8 inch drum travel at 30 feet per minute. It's usually a much higher rate. We'll talk about how machine speed, drum configuration, and pattern are interrelated and what it does to our surface. To jump to the other end of the spectrum, this is a micro mill drum. You can see how it is a very excessive amount of teeth. We no longer have these holders we talked about earlier. These are weld-on holders. So once we're worn through the teeth, in order to repair this, we would have to cut and weld on another holder rather than knock it out with our tools. But we provide a much smoother, finer surface. That is necessary for ultra-thin overlays. And that's what that looks like up close. This looks at the cost of the drum itself. Obviously, operation cost is going to go up because our production goes down. With that many teeth on the drum, the machine's not going to be able to move down the road as fast. It has to move slower to provide this sort of surface, but the weight and the amount of surface area that we've increased on the drum are going to hurt production. But aside from that, just the cost of the teeth alone, we see there how we go from 268 teeth to 770. When we replace that, our maintenance time to maintenance the drum goes through the roof. So all of this adds up fairly quickly. Now this is what production looks like with a standard drum on a full lane 12'6" drum. You can see at 2 inches with a standard drum we're around 60 feet per minute, and once you go down to a micro mill drum you're below 20 feet per minute. So it's a very significant production drop. And I'll move into what these two drums are here in the middle. For now we won't. But our standard 5/8 inch drum is a triple wrap, has 3 scrolls of teeth, and then each of the other 3 drums, the double hits and the micro, have 4 scrolls of teeth. So now we'll look at longitudinal smoothness. So how we achieve a smooth milled surface, and why a foot per minute at a standard drum you can still get a smooth surface, and why you can increase your foot per minute if you modify the drum configuration. So at first we'll start at 30 feet per minute. Now we'll keep drum diameter and drum speed in the top left static for each of these examples. Our drum speed stays the same, our drum diameter stays the same. All that's going to change is our advance rate, how fast the machine moves down the road. So at 30 feet per minute in one rotation of the drum, the machine's advanced 3.6 inches. So that same tooth, as it comes back around, leaves a very small residual material there. And that's what 30 feet per minute, another look at this, and you see the lines are nice and straight. Now what we've come to accept as more of a standard milled surface is really incorrect. You start to see a V pattern once we hit a certain speed. We call it a chevron pattern a lot of times, and that means the machine is outrunning the drum. Our forward propel speed of the machine is faster than the drum has to remove this residual material. So now let's move up to 60 feet per minute. Again, all we're changing is the machine speed, forward speed. So that same tooth, once it comes back around at this speed, The machine's traveled 7.2 inches. And now we leave over a 1/4 inch material behind. And the chevron pattern is caused by these pieces of residual material that line up, and they create that V. Now you start to see breaks in the lines. Okay, now we'll step it up to 120 feet per minute, and you're going to see a big difference. 120 feet per minute is not super common. It's certainly achievable by a list of machines, but 120 feet per minute is a little higher than what we typically see. But let's look at what impact it has on the surface. At this point, the machine has traveled over a foot between when one tooth on the drum hits the surface and by the time it can travel back around, strike the surface again. Now we've left over an inch, 1.16 of an inch behind. And that's when we see our chevrons really profound. You have all these breaks in the lines, and all that material left behind lines up to make the V. It's easy to understand or empathize why you would want to maximize your machine's productivity, why you want to get down the road as quickly as possible. Obviously, a smooth milled surface is in all of our best interests. It's in the best interest of the user, it's in the best interest of the paving contractor, it's in the best interest of the agency. So it's absolutely something we should pay more attention to. I just wanted to show you what this means to the contractor when you're at 30 feet per minute versus 120 feet per minute. 2.3 miles in a day versus 9.1 miles. Tremendous difference in production. And this is just to show you, we looked at a micro mill drum earlier. On the right here we have a standard triple wrap drum. On the left you have a double hit quad wrap drum. What we mean is within this drum you have 3 different scrolls of teeth that travel around this drum. On the left you have 4. So you see a larger number of teeth, but nothing like what we saw with the micro mill drum where it was so crammed in there. And what a double hit drum really means is how we looked at the animations earlier, and we saw that we were looking at the residual material left behind when one tooth struck and came back around. Now with a double hit, 2 teeth will strike within the same line. So in one rotation of the drum, 2 teeth are now aligned to strike the same line. So that residual material can be minimized by a double hit quad wrap drum. Just to sort of illustrate what we're talking about here, on a triple wrap drum, if you sat it down to where we're scratching the ground, when each scroll of teeth strikes the ground, we've got 1 tooth hitting each line in one rotation of the drum, all the way around. Now with a quad wrap, you've got 4 scrolls of teeth, and 2 will strike each line. And that's a pattern comparison at 100 feet per minute. 100 feet per minute is more of a production rate we see in the field. And you see we have this all too common chevron pattern here where we see the V caused by this residual material that aligns. With a double hit drum at the same advance rate, it's a much smoother pattern. Now, the double hit drums don't come without their own limitations, so they're not a solution for everything. This pattern really only is obtainable up to 4 or 5 inches. So at deeper cut depths, you would not get the benefits of it. At shallower cut depths, it's a nice tool to allow the contractor to achieve a higher production level, and everyone else, we get the smooth milled surface. But it's not a solution that can be applied to every project by any means. One of the ways that's different agencies, DOTs, look to ensure they have a milled surface or sand patch test. This is an ASTM test. Also the Indiana glass bead test is very similar. But the sand patch test is performed by dumping a known volume of sand onto the ground, and then they use a tool that's similar to a hockey puck. And this is spread out on the ground. And the specification is written to require a certain diameter. With a certain number of rotations of this puck, the sand should stretch out and you should be able to measure a certain diameter. If you have a very rough milled surface, the sand will not you can't spread the sand out as far. You can't reach the diameter that's required. So this is one way that has been done in the field, as a field check, because you don't want to require certain drums always. You don't want to force the contractor to buy expensive new equipment, but you also don't want to limit their foot per minute or their forward speed all the time, because that doesn't guarantee a smooth milled surface. This is a nice way to measure in the field and ensure that you can meet a performance spec. That's all I have for today. Thank you for watching. Appreciate your time.